Thank you very much. And thank you, Andrea, for inviting me for this nice workshop. So I'll present today some results obtained in the last few years with some collaborators involving some ice. They've seen something on a previous talk. And some of it is under some EPSRC grant. So yeah, I'll just go to some motivation and then we'll see a few different cases. So I'm going to talk about some continuous ice plate and some fragmented at the end in 2D and 3D. And I'll also talk about some internal waves under an ice plate. Just to mention the collaborators, so I have various studies or papers with all those people from here, various postdocs or PhD advisor or friends. And the background. So I started to look at these problems, I don't know, 15, 20 years ago maybe. And the motivation is, well, we wanted to see what happens when waves propagate under an ice plate or ice sheet. And especially at the beginning, it was what happens when you move a pressure on one of these ice plates. So people use the ice as a runaway or as road, and in all these northern regions like Canada or Russia or Antarctica. And for example, they land plans, and there is some interest in the safety of using this ice plate. Very recent, I found a nice paper, and some people from Canada are looking at again tracks moving across a lake in northern Canada, I think Gordon Lake somewhere, and they recording from satellite how much is the ice moving up and down, so that they see this wave field and they record this. Probably not easy to see. There are tracks going north and or south, and some of them are loaded and they go slower, and some of them are empty and they go faster. And there are various types of patterns. Sometimes this sort of like circular, well, curved patterns in front of them, don't going south, and the north are more localized. So this is I just came across that very recently, and the authors have done some more for the transport, Canada Transport Society or Association. And sometimes the things go wrong. So when I don't know, either going to the wrong speed, or you're going to maybe too loaded, or you meet some cracks in the ice, or so on. So sometimes they lose one of these tracks. So there's a lot of interest to see, well, when it's safe to drive, or how fast, or is there any speed which is dangerous, and to avoid it, or whatever you want to do. In some other cases, people want the opposite. They want the ice to break. And again, I think in the river in Russia, because in the south is hot, in the north is cold, they create ice and they want to break it, otherwise there'll be some flooding. And again in Canada, it's the similar problem. So they want to break the ice, and they use this sort of hovercraft. And you can click in one of these links, and you'll see how this hovercraft fly over the ice. And sometimes, if you go at the right speed, you can actually break the ice. And another ice-related problem. It's an observation of some sort of tsunami under ice. So there is a landslide in Lac de Saisiel in Quebec, some 100 kilometers north of Montreal. And this is where the landslide occurred, and then the waves propagated, and they're quite big waves. People say about 2 or 3 meters, and because they're too big, the ice can break. And the blue lines, you see the cracks, and I think the distance between the cracks is like 10, 15 meters. And you also see patterns. So you have this diffraction patterns when you have islands, and again, it's a complicated pattern. And again, people again want to see, I mean, how to predict this sort of waves. Related problems, which I'll talk a little bit later, it's internal waves under an ice sheet. So in some lakes, there is a stratification of the lake beneath the ice. So this is the salinity in various time of the year. So this is March, for example. You have a constant line here and another one here, with a transition between the two. And people see sometimes the waves on the ice cover, which cannot be related to the flexural forces, and they more likely manifestation of the internal waves. So we've done some calculations for some steady internal waves on the ice sheet. And again, very recent, we try to look at this problem. So what happens if a wave from the ocean go into this marginally ice zone, which is between the open ocean and the continuous ice sheet? And we try to see if we can estimate the attenuation of the solitary waves or some localized waves going into this into this field. There are a number of linear studies, but there are some observations which suggest that maybe also some nonlinear effects are important in this area. So Alice Kohut, for example. And the waves again are quite big, and it's well, the waves are getting bigger, and again they break more and more ice, and it's quite a big interest in this sort of area. Or what if you can predict somehow what happens with your wave going to this sheet, into this fragmented ice sheet. So those are the 3 or 4 different things I want to talk today, and I'm going to talk first, start first with a continuous ice plate. Okay, before that, I should say that I'm going to assume that ice, I'm going to model it as an elastic plate, which is true in under some conditions, and so it means I can actually use my theories to look for my theories, those theories. For other type of hydroelastic waves. When they have like very large floating structures, it was this floating airport in Japan or some floating island, if you read Jules Verne and so on. So initially, so we have a 2-dimensional ice plate, and apart from observation, people have done experiments in a variety of environments, in lakes or in the ocean, with water that's going from a very shallow, like in the in Lake Saroma, 6 point something meters, up to 300 meters in McMurdo Sound in Antarctica. And the ice can be again very thin or very thick, still thin compared with the depth of the water. They move various objects on the water and or planes, and they recorded what happens. And again, people have seen these waves very far from the border of the ice, and they're quite high amplitude. There is a good number of linear papers on this, of moving pressure in over an elastic plate, starting with Greenhill and continued to Cation and some other. More recent, some nonlinear results, which means that some sort of nonlinearity is used for the elastic plate, have been obtained numerically or analytically in the last, I don't know, 20 years, in infinite or finite depth. And I like to show always this nice experiment done by Takizawa in this Lake Saroma, when he moved I think ice skidoo with a constant speed, different speeds, and recorded what happens with the ice. And when you're very slow, this is what happens. You just see a small localized depression under the ice skidoo. And then when you increase the speed going down, you see some patterns forming, some waves starting to appear before or after this pressure, or just in front. And again, if you measure the depth of the deflection, you see that so this is the speed. This is how big is the trough, and you can find a nice curve, and you see a maximum of this deflection. And again, coming back to my first few slides, if you want to break the ice, you want to travel at this sort of speed, or if you want to not to break the ice, you have to not to travel this speed. And this speed will be very clear soon. What is it? It comes from the dispersion relation. So for the first, I don't know, maybe next 10 or so slides, this is the sketch of the problem. So we have an elastic plate, and you have some pressure or not on top of it. So sometimes I put the pressure and then I remove it just to obtain some free waves. We look for steady or unsteady waves with a different with different algorithms. We assume that the fluid is inviscid, incompressible, and flowy rotational. So I'm going to look for some velocity potential in the fluid. And you can use different elastic models for the ice sheet. You go some linear elastic models, or more complicated ones, or some viscoelastic ones. So we're going to use the elastic model, which I'm going to show very soon. So you have to solve the classical problems you've probably seen in various talks. So you have to velocity potential Laplacian in the fluid, some kinematic conditions on the elastic plate, and the Bernoulli one with the pressure, which depends on this elastic model you're going to use or not. So we use this Cosserat theory of hyperelastic shells satisfying Kirchoff's hypothesis. Basically, you have a thin elastic plate, the thickness does not change. The deformation, so if the normal lines stay normal to the middle of this elastic plate, you have some stored energy, and you can do a nice force balance and moment balance in the small piece of this elastic shell. For example, in this tau and q are the tangential and the normal tensions. P is the pressure. Q is the bending moment. So after some, well, not elementary, but still not very complicated steps, you arrive at some equation between this tangential and shear tensions and the bending moment, depending on the R length. We're assuming that the bending moment depends linearly on this curvature, which is what people use. And after some integration, you obtain the form of the pressure, which you are going to plug into the Bernoulli equation. So for people working on these water waves, you have this minus sigma k usually for the surface tension if you want to put only surface on top of the water. If you put elastic, if you use this elastic model, that's slightly more complicated, and it's even worse than the Cartesian coordinates in the last line. We make some assumptions, so we have no inertia. If you have inertia, we have to consider some other terms, some eta tt terms in the Bernoulli equations. No cavitation, so the elastic plate is on the water, there is no air between them. I assume there is no press tracing on this elastic plate, so I'm using this sigma to be 0. And I can first, I'm going to look for the dispersion relation to see the link between the phase speed and the wave number. And if you plot c against k, so we have the wave speed is c, the k is the wave number, we obtain always a minimum of the dispersion relation. And again, everybody from here is probably familiar with this capillary gravity case. When you have a weak surface tension, this is also the case for capillary gravity waves. But for ice, so when you have strong surface tension, this meaning disappears, but for the elastic plate, this is always there. And you have actually two critical velocity, the minimum, the C min, which corresponds to this peak on this amplitude of the wave below the moving load, for example. And have the long wave limit, the classical long wave limit, and those are the kind of critical speeds which people have observed in experiments. And again, just plotting that C min, the solid line is always lower than the dashed one, than the long limit. Now, I'm gonna, working with Philippe Guyenne, and we have rewritten the equations using an Hamiltonian formulation, which is basically extending Zakharov's formulation for water waves. And we introduced the DNO operator. So you can actually write it as in a nice Hamiltonian form, which are useful for some numerical calculations. And they're also useful if I want to do some asymptotics. I'm not going to see too many, but for example, when you're around this long wave limit, C0, you can do some scaling and expand Hamiltonian and so on, and obtain, under some conditions, some fifth order KdV, which you need if you want to include this elastic effect. On the other more important limit, the C min, the speed, You can apply again some modulation approach, and which was used by Craig, for example, Walter Craig and some other people. And you can derive after some work some nonlinear Schrodinger equations around this C-mean, and which is as you know, focusing if lambda mu is positive or defocusing. For elastic case, it changed the signs. If you have a deep water, you have a defocusing, so which will say there is no small amplitude solitary waves. And it's focusing for shallow water, which allows you to have this solitary waves. Now, for numerical computation, just a few words. So we take these fully nonlinear problems. We compute steady waves with some type of algorithms based on the Cauchy integral formula. And we calculate unsteady waves using this high-order spectral method. We're going to develop the DNO operator and truncate it for some number of terms and use FFT, and I mean, it's sort of classical. And that's what we obtain. So for the steady case, we do obtain solitary waves. So again, I was interested in waves generated by moving pressure, but again, sometimes if you remove the pressure and see what happens with the waves, so you obtain so-called depression solitary waves, and elevation based on what happens at 0 is less than whatever the mean level, call it depression. And in this lower graph, you can see some branches of forced waves when you have a pressure, the dotted one, or solitary waves when you have no pressure, the solid ones. A different feature compared with the capillary gravity case is that those branches start from, this is the critical speed, the C-mean, in the non-dimensional terms, at about 1.32. And we see that the branches start from a finite amplitude. And doing some calculations, you can go on the other side of C-mean and you'll find some sort of waves with non-decaying oscillations. But with these algorithms, we have to stop there. And the elevation branch is slightly more complicated than this one, so this is just the beginning of the branch. So this is the elevation branch corresponds to this solution. So this is in infinite depth. You can do the algorithms in finite depth. So we calculated both cases, finite depth and infinite depth. What happens if you move on the other direction when far away from the C-mean? So I'm on this region C less than C-mean. If I go to C goes to 0, I obtain these overturning waves, which obviously are not physical. So if you have to remember, we're talking about elastic plates. Self-intersecting solutions at C equals 0. So at some point, you have to stop your algorithms before this is happening. If I plot the energy or the Hamiltonian of this problem, if you look at the right graph, you'll see this is the energy of the depression solitary branch, and there are a couple of one minimum here and one maximum there, and again this may suggest an exchange of stability of the solutions, of the steady solutions, and this change a little bit when you look on the finite amplitude. This is different branches of depression solitary waves for changing the depth. So this is deep water, and this is very shallow. If you remember, the NLS predict for shallow water waves, small amplitude solitary waves, and indeed they start to bifurcate from 0 amplitude, as opposed to this case when they start to bifurcate from the finite amplitude. And this minimum of the energy branch disappears. Now, with the other algorithms based on this spectral method, we try to see what if we can obtain those waves and what happens with them. Are they sort of stable in this sense? So we're still in the case C less than C-mean. So we put a pressure and then we remove it. So in the first two graphs, you see the pressure moving to the right, and then we remove it. And you see that we still have this sort of coherent structures, the solitary waves, which is more or less the same as the one computed the steady algorithm, and some other radiations on this field. but this one persists for long distances. So we managed to obtain, in some sense, a solitary wave, and it does show that it's stable, well, in this sense, okay, numerical sense if you want. If I'm close to this C-mean, on the other side of this minimum of the energy branch, it's not that simple. So you do obtain the wave. So again, it's the first two are not, the first one, it's with the pressure, and then you remove the pressure. But this starts to decay much faster. So this suggests that this is not stable in this sort of area close to C-mean, which is in some sense similar with what happens for capillary gravity waves. We try to obtain an elevation solitary wave, and so we change the sign of the pressure. But it always wants to go to the other solution. So it seems to be that the elevation branch is not stable. Elevation solitary waves are not stable. What happens if I'm close to 0? So more recently, Tao and Jean-Marc have a look at this problem, and they've seen that again the solution is not. I mean, in time is not stable. So it's whatever self-intersecting and so on. So this is overturning solutions, which after some times looks like that. The other speed, the long wave limit. So here, what do we expect to see? So we put a pressure, we remove it, and you see these sort of elevation waves appearing, and I'm moving forward, and then some other dispersive waves. And those waves are not like proper solitary waves, but you do obtain these waves which seems to be, so they have this non-decaying oscillation in one side, which suggests some sort of general solitary wave. Which again, it is something which the fifth order KdV predict. Now this is a 2D elastic plate, 3D. So we try to again see what happens if we look at the full three-dimensional problem. So initially we started with a simpler model. So instead of having this complicated elastic terms, we use a bi-Laplacian, so we use a nonlinear flow and an elastic plate model. We use the boundary integral method, which is based in Green-Stecon's formula, and it was developed by Forbes and some other people before him for gravity waves. And so you have to solve basically these integral equations and the Bernoulli equation. And at the end of the process, currently we also want to do something else. We want to put a full nonlinear elastic model in 3D, which involves this mean curvature H and the Gaussian curvature kappa. So this is still work in progress. And this is what you obtain for if you have, again, forced means that you have a pressure moving. I'm looking at waves with a speed less than c mean. So the waves moves across this x direction. And when I'm approaching the c mean, you see more and more oscillations appearing. And also you see signs of truncation of our computational domain at the border. And we hope to obtain solitary waves if I remove the forcing. So for the linear case, we did obtain something like that. This is computation done actually by Olga Trishenko, a postdoc which worked with Jean-Marc, Paul Milewski, and me. And we're in the process of trying to obtain the same stuff for the nonlinear elastic model, and again, try to obtain some solitary branch in 3D. What happens if I move on the other side of C-mean? So if you remember when I show you these tracks moving south and north, I say that if they go slow, you have just some localized patterns because they travel with C less than C-mean, or U less than C-mean. If they travel too fast, faster, you see these patterns in front or maybe behind of the tracks. So you can do a linear theory, and they've been done by Davis and Hoskin and some other people 30 years ago, and Milinazzo 20 years ago. So here on the left, you see paths, so you see pressure moving to the right in 4 cases, and you just increase the speed. And you see waves curved in front of the pressure, and kind of Kelvin-type waves maybe a bit behind. So again, if you look at the patterns in 3D for capillary gravity waves, you'll see some similarities. So the waves in front of the pressure are mostly dominated by flexural effects, the one behind the combination of gravity and flexural effects. So on the right, you see some calculations done by some rectangular load. Again, everything is linear in this case. So we try to see if we obtain solutions using computing fully nonlinear 3D waves. And the answer is yes, we could, but we have to use some small numerical tricks, like putting some artificial viscosity. Otherwise, we have some reflection from the boundary. So in this case, we have a pressure moving this way, like your truck from the beginning. And you see this kind of Kelvin kind of stuff start to form behind the pressure. And you see these curved waves in front. And again, you can vary the speed to see how this pattern varies. So this is what we've done in 3D. Again, this is, I should mention, this is done with an elastic plate model. So this is in the simpler case. So for the non-elastic model, it's slightly more complicated numerically. And now going to the internal waves. So far we've seen just one elastic plate in front on top of the water, which is finite depth or infinite depth. Now, what happens if I have a stratification under the ice plate? As I mentioned, in the lakes, you see this quite, if you measure the salinity, you see the stratification. So we try to calculate waves in this configuration. So we have an elastic plate on top, which we use the previous model for the elastic plate. We have a stratification. We have a two-layer flow, which is one of the simplest models. I should also mention that recently we extended this model, so I didn't have time to include this one. When they have some satellite over the Jupiter and they look at the Ganymede moon, they saw some structures. They infer to be some stratified oceans and a layer of ice. So you have ice, ocean, and so on. So you can actually complicate this model and actually put an elastic plate here if you want, and so on. But for what you'll see next, this is just elastic plate on top and a interface between the two fluids. So with two densities, ρ1 and ρ2. The problem is more complicated. You have these two unknowns, so you have more equations to solve. And the simplest thing to do is first to look at the linear case to find the dispersion relation. So I'm looking against C against K. Having stratified flows, you have two so-called modes, or baroclinic or barotropic if you want the other termination. So you have a slow one, which starts from here, from K equals 0, the long wave limit, or a fast one. And I'm usually looking for solitary waves, and you try to find a gap in this spectrum. And I'm looking between these two, this minimum and this sort of long wave limit for the slow mode. And we did obtain solutions in bifurcating from both, from the minimum or from this sort of long wave limit. They are slightly different. The one bifurcating from the upper plate, sorry, not plate, from the upper mode. So the slow mode and fast mode, they have signature on both upper and lower one. So the waves bifurcating from the fast mode, from the minimum of the fast mode, they're in phase, and you can see that this is the elastic plate deformation, this is the interface deformation, and you can actually push them quite hard, so they're almost touching each other. And you can see both types of them. You can see the so-called depression ones, or you can see elevation. So we see elevation on both the upper and the lower, sorry, on the elastic plate and on the interface. If you bifurcate from the other one, so this one should go back here. So if you bifurcate from these values of the fast mode, of the slow mode, sorry, the waves are out of phase. So you see an elevation on the elastic plate and the depression on the interface, which is, and again, I'm using kind of realistic density ratio. So this is 0.9. I can go to higher, 0.99, which is close to what happens in the oceans. And the interface has a much bigger amplitude than the deformation of the elastic plate. And again, depending on the ratio of the depths of the two fluids, you can find elevation on top, depression in the middle, or the other way around, depression on top or elevation in the middle. Now, we can also play with the parameters, so we can make, this is the dispersion relation on the left. If I want, I can make a maximum appearing on the dispersion relation, which will means that the slow wave starting from there will have decaying oscillation. So this is the kind of wave starting, which bifurcates from this maximum of this lower dispersion relation, slow mode. I should say this is slightly more realistic. This is the density ratio is quite small in this case. What happens even more interesting in this case is I can start with some waves which are out of phase, starting from here and going up and crossing the minimum, and I obtain the so-called generalized solitary waves, which are waves with no decaying oscillations. I mean, the numerical method is actually, I'm calculating long periodic waves, and I can show that I can put more and more of this oscillation and nothing changes. So this is the numerical trick. But because I have a wave which meet with two sort of waves bifurcating linear, waves bifurcating from the linear dispersion relation, you'll see two different type of wavelength on this tail. So for people familiar with the interfacial waves, gravity waves, usually you have only one, because you have only one of these small waves traveling with a big pulse. But here you have this big pulse, and you have these two different kind of wave with different wavelength interacting each other. So again, this is a half of the wave we have. This is symmetric and so on. And I should mention there are some also non-symmetric waves, but here is only everything is symmetric. Okay, so this is what happens for the internal waves. Now the last topic for the next, I don't know, 10 minutes or so. It's what happens if we try to see what happens with a wave when it meets a fragmented ice sheet. So the question is how to model this thing. So we have our model, which is, let's say, a first model, which can be improved and should be improved. We put a function in front of these flexural terms, and the function can be 1 if I have an ice flow, or 0 on the free water. Now this will have all sorts of problems for the numerics because it will be discontinuous. So we have a tangent ramp between the two. So it will be a region between the free water and the ice flow when this function goes from 0 to 1 continuously. So this has the advantage that I'm sort of combining the continuous approach with this model. There is a disadvantage is I cannot move my ice flow, so my ice flow stays at the same place because of this function f. So there is no feedback from this ice to the wave. So again, this can be changed. Because I'm using also a function of x, it's probably better to use a function of the r length, so you can keep this constant. But okay, this is a model which we're using now. So first, we try to compare the boundary integral method results with an unsteady one to see if you obtain the same thing. So first, we have only one ice flow. So we have wave. Well, to create waves, we needed to put a pressure on this ice flow. So if you imagine you have a bear on the ice flow and the current underneath, or the bear going the ice flow otherwise, and they move to the right. Because you have flexural effect on the ice flow, you should have waves, flexural waves in front of the pressure, or what you put. So we have these blue waves here, and the big pulse correspond to the pressure. And it's the same case for two different speeds. So I'm in a very shallow water, I should mention. And the red ones are the results obtained in the unsteady method. And they seem to predict very well the big pulse corresponds to the pressure, and also the first few waves. And then because of all this radiation which accompany our unsteady method, we have to stop at some point. But it seems to show the same result. So encouraged by this, we say let's put now model of fragmented sea ice. So we choose a number of ice flows, which is NF, with some length, LF, for example, and between, let's say, 100 and 500 in our computational domain. To be more realistic, we randomize them a little bit, so each of them is multiplied by some number between -1 and 1. And we can cut them if they get out of of this field, of this 100, 500 computational field, or if they collide it, we can have longer ice flows, which again kind of correspond with what happens in the field. So that's our model, and this is what we see here is the function f of x, which is 1 against when it should be an ice flow. It's a tangent between them, so the tangents go from 0 to 1 across I don't know, a few number of mesh points. And so what we want to send a solitary wave. So that's why I'm using shallow water. So we compute the shallow water, for example, using Tanaka's method. We send it to this ice field and see how much it attenuates. And that depends on this attenuation on this configuration of the concentration of the ice flow, or how long they are, and so on. So that's our goal. So where the numerical method we use, it's similar with the one you've seen before for the continuous ice plate. Now, this is no longer Hamiltonian, but still you can use the same sort of numerical method. And you can vary the parameters, so you obtain a solitary wave in shallow water with some height a, which you can vary. You can vary the ice concentration, you can vary the ice fragmentation. And we try to see if our numerical method gives results which kind of look realistic. And we look at in two norms. We look at the maximum elevation, and we look at sort of scattering. So we use the L infinity and L2 norm of the eta. And here is an example of a result. So on the left, so this is the first one is the wave before entering the ice flow field. The red ones are the ice flows. So in this case, as you can see, the ice flows are quite small, so it's quite fragmented. And then we follow this wave, and again you have to look at the 100, 500. So this is just this period, this computational part, and you see all sorts of interaction, all sorts of reflection happening here between so wave scattering due to the ice flows. But you can follow the solitary waves. So the solitary wave is decaying because of all this interaction between ice flows and the wave. And so the pulse, there is some energy loss of the pulse due to this radiation due to the multiple reflections. So again, in this case, we had let's say 31 ice flows length 4. So it's quite a lot of open water. Here we have less open water. We have the same number of flows, but they're longer. And you still can see the same pulse, but it's more spread now. And if you put actually more, this is the other case when we have a few ice flows, but they're quite long. And you see this, it's a different way of losing the energy, if you want, of this main pulse. So it's some ondulation which appears on the ice flows, which is due to the flexural effects. And again, this is another realization. So you can sort of follow still what happens with your solitary wave on the red ones. And again, the free water is the blue one. So there are two effects. There are this scattering of wave due to these ice flows in some cases when you have a very fragmented ice sheet. Or you can lose the solitary wave is attenuating due to this ondulation which disperses on wave packets in the ice flows. And this is an extreme case when you have just an ice flow. So basically you have a solitary waves coming into one continuous ice flow. And you see the poles here, and you see these waves in front of them, which again it's due to this flexural effect, and because you're in the shallow water regime. And this is just to convince you that actually it's continuous. My solution is continuous between the open water and the ice flow regime, which they should, because that's what I'm using my function f of x. Now we can have some conclusions. We've done various runs, and for different amplitudes of the solitary wave. So we started the small one, 0.01, up to the 0.3. So this is for some case, 31 ice flows, length 8. And we plotted some linear fit and exponential fit, and in some cases the linear fit is better for the smaller amplitude of the solitary waves. And the red one is for a single flow, and the blue ones are for this 31 flows, length 8. You can do this is the L infinity norm, just measuring the maximum elevation. You can do the same for the L2 norm. So and again, this is more, as you may expect, closer to this fit, this linear fit and the exponential fit. And again, if A is bigger, you have a stronger attenuation. So our model kind of reproduces what we expect to see from the ocean. We put together a number of data, and we actually use a two-term exponential fit, because our data don't seem to go to 0, so they go to some sort of non-zero values. So we try to say, to ask the question, to answer the questions, what's the most attenuating? If you have a lot of ice flows, but they're smaller, or fewer ones, which are longer. So we found that, for example, this configuration, which is the red one should be, the triangular red ones, is the most attenuating between the 4 configurations which I was looking. And if you have too much open water, this is least attenuating, the blue one. And I mean, you can look at all sorts of things. You can again now plot what happens with your when you change the amplitude in all these scenarios, or you can change the concentration of the ice. And just a few results, what we actually say mostly in the last 5 or 6 minutes. So if you have a large wave, it have a stronger attenuation. For small waves, it's better to use the linear approximation. The attenuation is more linear. And for large wave, sometimes you need a double exponential function of time. And if the ice cover is partial, the wave attenuation is weaker. So this is what I wanted to say. Just if you want to see more about the sea ice, in 2 weeks we'll start another big program here for 4 months. It will have various things in sea ice, and the most close to what you've seen today in my talk is the October ice fluid interaction workshop, when there will be people talking about hydroelastic effects and so on. And I think, thank you.
Any questions or comments?
I have questions.
Yes.
So when you say you use the Hamiltonian framework and try to take advantage of it, does that mean like somehow in terms of integration, use like a spatial integrator, like a symplectic integrator or something like that?
No. I mean, the Hamiltonian used to obtain this approximation model like NLS and the fifth order KdV, and then we just no, we don't use that much,
Okay, so it's more
because the last results they're not Hamiltonian actually, because
Okay,
yeah.
So
No, it does numerical.
Using spatial
No.
Any other question?
Or maybe you can ask another one. Okay, in the beginning you showed the profile like with the depression. Could you maybe go back more, like maybe first, third depression of curiosity, numerical curiosity? When you showed some numerical results, maybe more towards the half part of your talk. Let's see, I'll point out. Please keep on going. Please a little more. Yes, there.
Okay.
So you have not necessarily depression. So the bottom 2 graphs
Yeah.
behind, say, the highest sort of pulse, right?
Yeah.
it seems to be noisy, right? Is that numerical noise
It's
because
not-
of the
it's-
steepening or
It's
not?
not noise. You can find, so if you plot the dispersion relation in this case, remember now. So if you plot like C against K, it's something like that. So we're in this sort of situation. So this wavelength, the wave number or the wavelength, correspond to this sort of wavelength, to this sort of small
So
oscillation.
short wave.
Yeah, yeah. So you have a big pulse which correspond to whatever, starting from this long wave limit, and it travels with this sort of small wave, smaller wave.
Are these short waves physical, or you're saying that they are physical, not numerical? It looks a little bit like unstructured.
They seems to be there, so even if you change scale
Even if
and
the
so on.
resolution changes, okay, so there's there.
Yeah. So they seem to travel together. So in the theory of general solitary waves, you have the symmetric ones, but because of the physical, you cannot have waves energy coming from infinity. We see them only on one side usually.
And then does that have to do with the fact that this sort of pulse, if it gets thinner, these guys are bigger, like the steep profile nearby affects it or not? Just curiosity.
Good question. I don't remember now.
Okay.
Yeah.
One question. I suppose you discussed a little about wave training.
Yeah.
It means it's not important in this case.
The wave trains.
Wave training.
We didn't consider on this, no. So I mean, I was more into this sort of solitary waves and stuff.
Yeah.
Yeah. They may be important, but we're not didn't look at this one.
In the beginning of your talk, you showed a slide showing periodical clocks on the ice.
Yeah.
No, in the beginning, just the beginning. Yes, this one.
This one? Yeah. I mean, yeah. So this, so let's say this is we have a wave, sort of tsunami-induced wave, if you want, and they just travel, and generally sort of periodic waves.
And
Yeah, we didn't look at this sort of problem.
like we wave training.
Yeah. I mean, I mean, people seen this sort of so you see these waves traveling with the. Yes, so there are wave trains on this one, yeah.
Any other questions? Okay, so thank you very much.